So the building is outlined on a west to east axis point. So you have a lot of south-facing glass, north-facing glass, and a minimal amount of east and west glass. And you can see around the south-facing windows there are bonded structures to temper the building from the overhead sun. You'll see there's an east and a west vertical shading element there, and that breaks up the east and west beam. And then the horizontal shading element, that allows for additional daylighting inside the building, as well as tempering the building from the overhead heat. So if you translate that to a residential situation, if people are designing new buildings, you know, that dream home or that cottage or a new residence, what they should try and do is, if possible, orientate the entire structure so that a majority of the window glass will be on the south and the north. You want to minimize as much as possible the east and west glass, and that will control, you know, energy gain on a season and energy loss on a seasonal basis. And that's what NREL has been doing here. And you can see where you do have east-facing glass, you can either use more energy-efficient windows, and there are things like electrochromic windows in this building where you can, with a push of a button, darken your window glass. And these are today still very expensive compared to conventional windows, even Energy Star windows, but they have excellent U factors and they are available. But there's also shading elements that can be used, and this can even be done inside a residential construction. You can either temper the building on the outside with a shading element, or if you have more control, don't even put the window glass in on the east and west if you can help it. But if you are by code required to have so much window glass, you want to use the most energy efficient windows you can afford to do, or inset those windows into the wall to create a shadowing effect. This building also has some unique cooling features. Underneath each wing of the building is a cement labyrinth. And so these are slightly above grade here because of the nature of the expansive soils on this campus. But you can still use the energy of the earth in a passive sense for heating and cooling. And what they're doing is they're bringing in fresh air from outside, and they use the labyrinths underneath the building as a temporary storage area for this airstream. And so the labyrinths themselves were bio-inspired. There's a cross-section of a mitochondrial organelle. And when you cut those in half, there's these folds inside the organelle. And what they've done here is mimic that with concrete. And so it almost looks like a maze of concrete down underneath each structure. And that will be a place to store the waste heat coming from the computer servers in that wing. And in this very first wing, on the south side, is a transpired solar collector that was invented by the laboratory. And so a transpired solar wall can preheat the air for a building. It can easily be outfitted on a conventional building like a factory, any kind of manufacturing complex, even a supermarket. And in a residential situation, it might not have the largest application, but in any building that has a large south-facing exposure, you can put a transpired solar collector on it and actually tie it to the HVAC system of the building and preheat the air for the structure. And that's what that one is going to do. It's going to provide preheated ventilated air for the very first wing of the building. So couple that with energy efficiency and you use less heat for space heating. And this entire building, like all the others that are behind it, actually use wood chips as another heating source and natural gas as a third source of heating. Even human body heat in the building can provide some heating. You know, when people are working at their computer, they give off body heat. That actually helps heat the building. You'll notice that in the middle of the building, there's quite a bit of East glass. And that basically serves as a shading area so the building doesn't get as hot. The whole roof will provide, several hundred kilowatts of electrical energy from the PV system.